circuit. So it consists of a BJT. So what is BJT here? BJTs are bipolar junction transistors. They have, we have NPN or PNP, N as in, N type and P as in P type. So we use NPN as an example. We know, that, NPN BJTs are, a sandwich of N type, P type, and N type semiconductors. So we have collector, which is N, base, which is P, and emitter, which is N. And, this is the symbol of a BJT. We have collector at top, and then we have a base on the left, and an emitter at the bottom. So there is an arrow at emitter, which indicates the direction of current. Okay, so if you are curious, what is really in a BJT? What is really in that piece of some, silicon? So this is, a cross-sectional view of a, NPN. You will see, there's a heavily doped region, which is N plus. This is your emitter. Then underneath this emitter, there's a, P region, which is the base. Then, underneath the base, there's an N-type collector. So this is really a sandwich here. All right. So, BJTs are really complicated. Many people, spend their entire career, developing and studying transistors. And again, transistors also won a Nobel Prize. So we are not going to go very deep into transistors. We will just scratch the surface. What we can see here is that, there's a P, there's an N. So this is essentially a PN junction. So to turn this PN junction on, you want to apply a voltage that is greater than their forward voltage. And for silicon, this is 0.7 volt. So when you apply voltage greater than 0.7 volt, the BJT, the PN junction turns on and the BJT turns on. That's the first thing you want to know. Then how do we use this BJT as a switch? So to function like a switch, you want the BJT to have, to just, appear like, a wire in your circuit. That means you want the voltage across the collector and emitter to be around 0 volts. That's how your BJT looks like a switch. You want to make sure the voltage between collector and emitter to be around 0. And this condition brings our BJT to something called a saturation region. So what is the saturation region? We will not go very deep, but this is one of the operation mode of your BJT. So we know that when the base emitter voltage is less than 0.7 volt, the BJT is turned off. Once it's about 7 volt, there are 2 operating modes. So when VCE is greater than VBE, then your BJT enters active region. And in active region, the collector current equals beta times base current. This is actually how we normally use BJTs. We like this property because, in this mode, we are essentially amplifying the base current by beta times. This is how we normally use BJTs. But, this is a switch. So we want VCE to be around 0. So this makes our BJT work in the saturation region. And the key characteristic of the saturation region is that your collector current will be less than beta times IB. So this is what we want to do. Go ahead.
When you say saturation, is that talking about the recombination? Like it's fully recombinant or recombined?
That's a good question. I think the saturation, you have a point to add?
No, I was going to ask something after.
Oh, yeah. Okay, I think the saturation here means that, again, I'm a little rusty, but let me try to explain. So, so your PN junction is, when you apply voltage, your PN junction is generate a lot of electrons and holes. And then, the base collector there's also a p-n junction that is pulling the electrons and holes. I think it's electrons pulling the electrons to the collector. So that's why it's called a collector. So in the saturation region, that means, that means we are pulling the, we are pulling the electrons so fast, that we reach, we are pulling the electrons not fast enough, so that, since there's a very small voltage here, so we are not pulling the electrons fast enough, so their recombination reaches saturation. I'm very rusty. I learned about this like 10 years ago. So if I'm wrong, correct me.
Okay.
So what matters for the BJT is just
Mhm.
the potential difference across either the base and the emitter or the collector and the emitter. And
Yes.
depending on which is higher,
Mhm.
the current will flow from that junction.
Yeah, say that again.
So like potential difference determines like where the current will flow from,
Mhm.
right? So it's basically just switching between the collector and the base,
Collector and the base.
like whichever current to like pull from.
Well, the current will always be flowing this way.
Okay.
Current is also always flowing this way, but depending on which region you're working in, so there's a potential job between the collector and the emitter.
Yeah.
And to use it as a switch, you want to eliminate that voltage drop.
Okay.
So that's why we try to bring it into the saturation region. Just make this zero.
Oh, so if it's not in the saturation region, it can't work as a switch at all. Instead, it would amplify current.
Well,
Beta always usually above 1 or below 1.
It's always above 1.
Okay, so it does amplify.
Yeah, it does amplify. So I think you were talking about the current characteristic.
Yeah.
Yeah. So for switching circuit, what we care is the voltage drop here.
Mhm.
So we make it 0 so that it doesn't affect the operating of the circuit at the top, because there's a 0 voltage drop here. You don't lose any voltage.
So if 0 voltage drop, it becomes the control logic that we want.
The control logic is always at the base.
Okay. And we
Yeah.
need 0 voltage drop for it to function like that.
Oh yeah, I think you get it. Yeah. So the control logic is always at the base. So okay, so for the BJT switch, we want to make sure the collector current is less than beta times the base current. That's what we want to make happen. So to make this happen, we first need to derive the current of IC and IB. So, and once we have these two formulas, we can have a formula like this. We want to make sure IC is less than beta times IB. Beta is typically like 100 to 300 for BJTs. So to be very safe, we will just force this bit to be around like 5 to 20. So let's just make it 10. So this is how you design your switch in your lab. Derive formula for IC using Ohm's law. Derive a formula for IB using Ohm's law. Then you want to make sure IC equals about like 10 times IB. Okay, so how do we get IC and a bit IB here? Let's spend like 3 minutes